Hi everybody. So today I want to talk to you about relative velocity, and as always we're using Giancoli's Physics Principles with Applications for this course, Physics 1103, and in this lecture I'm also drawing on some ideas from Surway and Jewett's text, Physics for Scientists and Engineers. So what we're talking about when we talk about relative velocity is we're referencing something called Galilean relativity. So we're already familiar with Galileo from his work on kinematics, and he also described the idea of relativity. And this idea is that a physical event, if something happens, a physical event occurs, you have to have a frame of reference or a coordinate system choice that you use to establish and lay out the basics of the problem. Okay? Now, the idea is that you need to choose a reference frame that's not accelerating. So it's a frame that's either traveling along at a constant velocity or it's still. Okay? These types of frames are called inertial reference frames. So, for example, if you're on a merry-go-round going around in a circle, you're constantly changing direction. And so that would be an accelerating reference frame, which would mean it's a poor choice from a Galilean perspective. Okay? So you need a constant velocity or a still frame in order to have a good reference frame so that the physics makes sense according to everything that we've been talking about in class. And then if you choose a reference frame that's got these properties, that's an inertial reference frame, then the laws of physics should be the same no matter which reference frame that you use to describe it. So as an example of that, let's think about what happens if you've got a really poor safety choice going on and you have your child in the back of your pickup truck, not strapped in at all, and this child is taking a ball and throwing it up and down. Okay? From the perspective of the child, the ball just goes straight up and it goes straight back down into his hands when he tosses it. Alright? So he could set up, if he chose, some physics equation to describe it, and it would be just like that free fall physics that we've been talking about for motion in one dimension, where the ball goes up and it comes back down. Gravity would be measured as 9.8 meters per second squared down. The motion would be described by the kinematics equations. Everything would be happy. Okay, now let's talk about the perspective of someone that's sitting on the side of the road watching this kid go past in the back of the truck, probably judging the parent for a really poor choice on where to place the child, right? Okay, so in addition to the judgment calls about parenting styles, they could also watch the ball's trajectory. Now, from the perspective of the person on the side of the road, the ball is going up and down. They would both agree on that. But according to the person on the side of the road, it's also moving at a constant velocity in the x direction, assuming that the truck is moving at a constant velocity in the x direction, of course. You don't want an accelerating truck because, like I said, that's a poor choice of a reference frame. So we're assuming that the truck is traveling on a straight road at a constant speed. Okay? Now, from this observer on the side of the road, the path of the ball would be parabolic, as it would be described by the kinematics equations in two dimensions. Okay? So, the laws of physics are the same in all the reference frames, right? You use the kinematics equations to describe the physics, the ball going straight up and down, and you use the kinematics equations to describe the ball traveling in the parabolic path. Physics wins either reference frame, and you don't need to make up new physics to describe what's going on. So, the two observers might disagree on the shape of the ball's path, but they both agree that motion obeys the law of gravity, Newton's laws of motion are obeyed, they agree on how long the ball was in the air, and so the conclusion is there's really no preferred frame of reference for describing the laws of mechanics. But if you're shifting from one frame to another, you have to be able to do that and not break any physics laws. And so that's where we're going with it today for our lecture on relative velocity. Relative velocity just means that the velocity relative to a particular frame of reference, okay? So, if you're talking about the motion of the ball, for example, you need to say which frame of reference you're describing it with, and then you would give the velocity relative to that frame of reference. If you change reference frames, your measured velocity may change, okay? So, for example, at the top of the trajectory for the kid tossing the ball in the air, right, the kid would say that at the very top of that trajectory that its total speed is 0 for a second, right? Just a split second when it reaches the top and turns around to come back down. However, the guy watching the truck on the side of the road would say, no, the ball's speed is never zero. True, at the top of the trajectory, its y velocity is 0 for a split second, but it's still going in the x, right? So that means its speed is different. So you have to understand which reference frame you're talking about when you talk about what the velocity of the particle is, because it might be different from frame to frame. Now, your textbook uses a certain convention for how these things are written out to indicate the object and the frame. Each velocity is labeled with subscripts, and in the subscript, the first letter will indicate the object that's being referenced, and the second will indicate the reference frame in which it has that velocity. Now, we're going to go with a convention that you've got a relative velocity that you're trying to find, and you want to find the velocity of object A with respect to reference frame C. So that would be labeled VA sub C, right? A for the object and C for the reference frame. And of course the arrow across the top is to show you that it's a vector quantity, so it has a magnitude and its direction. Now, the equation for relative velocity reads this way: VAC equals VAB plus VBC, and those are all vectors. So if you were to say in words what this means, it says the velocity of object A with respect to frame C equals the velocity of object A with respect to frame B plus the velocity of frame or object B with respect to frame C. So that's kind of hard to think about until you start applying it. So let's do a couple of example problems so that we understand what's going on here. Let's do a really simple one first so that we can just understand the equation and how it's applied. So here's the simple example. A person on a train traveling 100 miles per hour runs to the bathroom at the back of the train car. They run at a speed of 6 miles per hour relative to their seat. So what's the velocity relative to an observer that's standing beside the train track, right? So what's the velocity of the person that's running to that bathroom with respect to the person that's standing on the side watching the train go by? So let's think about our equation that we had there and identify what is what, okay? So we're going to call object A here, that's our red smiley face. That's the person that's on the train that's running at 6 miles per hour relative to the seat. Frame C is the stationary frame of Mr. Blue Smiley, right? And the object or frame B, that's the train's perspective, okay? So the two reference frames are the stationary frame on the side of the road, right? That's frame C. And the moving frame, the constant velocity frame of 100 miles per hour of the train, that's frame B. So if you were trying to identify what goes where, VAC would be the velocity of the red smiley guy with respect to the stationary frame, which is blue smiley guy. So what would blue smiley guy see as object A's speed or velocity? Okay, that's this first term in the equation, and that's what we're solving for. Now, we're given the speed that the red smiley runs with respect to his seat, okay? Now, in terms of the velocity, that is towards the back of the train at 6 miles per hour, and I've indicated that with this arrow, this short arrow that points towards the back of the train. And the magnitude of that velocity is 6 miles per hour. Now that 6 miles per hour is with respect to the train. And so I've drawn an arrow here, VAB, from the vector quantity in the equation to the smiley with the arrow, the short arrow indicating. So VAB, that'll be our 6 miles per hour towards the back of the train. So we've identified that. Now, the next quantity is VBC, okay? So that is the velocity of frame B with respect to frame C. So here, frame B is the train, and frame C is the side of the tracks there, the stationary frame. So I've drawn an arrow here from the vector quantity BC in the equation to the arrow that indicates the direction and magnitude of the train's velocity. All right, so that identifies that. Okay, so now that we've identified what each one of these things in this equation are, Now let's go through and solve, okay? So of course we're going to take the standard convention, which is to the right is positive. This is a one-dimensional problem, just to start off with something easy. So to the right is a plus positive quantity, and to the left is a negative quantity. And we don't have any other directions to worry about, so we're done there, okay? So VAB, that is, okay, so VAB, that is 6 miles per hour towards the back of the train, so that's negative 6 miles per hour. That's what we're plugging in for that. VBC is the velocity of the train with respect to the side of the tracks, the stationary frame, and that's plus 100 miles per hour, so we plug in for that. And now we're solving for what the velocity of the red smiley guy would be according to blue smiley. So that's minus 6 miles per hour plus 100 miles per hour, which gives me plus 94 miles per hour. So the dude on the train that's rushing to the back in the bathroom, he looks like he's going a little slower than the train because he's traveling opposite to that direction, okay? Which makes his relative velocity for the blue smiley guy a little lower, all right? Hopefully that's pretty clear, but if not, pause it for a second and stare at it until it makes sense to you. Okay, let's do a harder example, and this one we're going to have a two-dimensional kind of thinking going on. So let's read this together. A person is trying to swim across a river which is flowing at 2 meters per second. In still water, they can swim 1.7 meters per second. So what's their speed in the river with respect to the bank? And how far downstream do they end up when they reach the opposite side if the river is 10 meters wide? Okay? So it's a pretty big river there that they're trying to ford. Okay, so I've drawn myself a picture to help us visualize this problem. If they're swimming across the river, then I'm going to assume that their velocity is perpendicular to the river's flow. So here I've shown downstream as to the plus x direction here. So I've shown the water as traveling 2 meters per second, and that's what that arrow there indicates, 2 meters per second to the right. Now, the 1.7 meters per second, that's straight across the river. So that's the direction the person is trying to swim, okay, straight across the river. So they're going to kick and push the water with their arms as hard as they can straight across the river, all right? And I've also indicated the width of the river here as 10 meters, which means that this red smiley guy has an enormous head. No, I'm just kidding. But anyway, it's not to scale, okay? So we have our two vectors there, and you can see that they're perpendicular to one another, indicating that this is going to be a two-dimensional problem, okay? So let's identify what each one of these variables is in our relative velocity equation. Yet again, we're solving for VAC. That'll be the velocity of object A with respect to frame C. Let's identify A, B, and C. Here, object A is the red smiley, the swimmer that's trying to make it across the river, okay? Frame C is the stationary frame on the riverbank. And the object, or frame B, that's the water in the river that's traveling to the right with 2 meters per second velocity, okay? So those are our variables. Okay, let's choose a coordinate system. If I choose the origin of the coordinate system as where the red smiley guy first jumps in the water to swim across the river, then that's a decent choice. I'm going to have my x direction being parallel to the flow of the water in the river, and my y direction being parallel to the direction that red smiley is trying to swim, straight across the river. So that's my coordinate system choice there that I'm making. Now, let's look at each one of these things in turn. Remember that in a two-dimensional problem, you have to take the x components and the y components of each of your vectors and resolve those components. Now, since these components in this case are directly aligned with the x and the y axes, that makes our job a little easier. The person is actually trying to swim in the plus y direction, okay? So, in this case, the VABX, that's equal to 0. Because they're not moving in the x direction on purpose, right? They're trying to swim straight across. And VABY, well, that's the total speed that they can give it, 1.7 meters per second. So their velocity is going to be 1.7 meters per second in the plus y direction. Now the river, it doesn't flow in the y direction. We're assuming that the water flows straight down the river, so it all flows in the x. So if we take the components there, then the velocity of b with respect to c, that's the velocity of the water with respect to the stationary bank, then that's 2 meters per second in the x. And it's got no component in the y direction because the water doesn't flow in that direction, so it's equal to 0 there. Okay? Okay, now remember in vector addition, we're going to take the x components and add them up, and then take the y components and add them up. And we're going to add them separately. You don't add x components of a vector to the y components of a vector. That's a big no-no. Alright, so when we get VAC equals VAB plus VBC, we're going to separate that out into two separate equations, one for the x and one for the y. So here, VACX is equal to VABX plus VBCX. Okay? So, remember, our x components were 0 and then 2 meters per second respectively. So it's 0 plus 2 is equal to 2 meters per second. Next we have the y equation, and that's VACY equals VABY plus VBCY. And so that is 1.7 meters per second plus 0 is equal to 1.7 meters per second. And that gives us the y component of our final velocity. Now, if you do the tip-to-tail vector addition, you can see that you have the y bit here, the 1.7 meters per second, and then you put the 2 meters per second at the end of the 1.7 meters per second vector, and it goes straight over. And then your resultant vector is indicated here in red, connecting the beginning of the 1.7 to the end of the 2 vector. Okay? And then that gives us our final equation, our final drawing for the relative velocity of the swimmer. So what's happening here is the swimmer is trying to swim straight across the river, but because the water that they're swimming in is moving itself, it carries that person downstream. So now that we have the components of the vector, we can solve for the speed. Remember that the speed is the magnitude of the velocity vector, which is the scalar associated with it. So the magnitude of vector AC is going to equal to the square root of the sum of the squares of the x and the y components. So that's the square root of VACX squared plus VACY squared. The x and the y components are 2 and 1.7 meters per second. So that's the square root of 2 squared plus 1.7 squared. And then once you take the square root, you'll have meters per second again. And when you do that math, it turns out to be 2.6 meters per second. So that's the speed with which the swimmer is going. According to someone that's standing on the bank, if they had like a motion sensor and they tried to measure the speed there, that's what they would get. So you can see that that speed is larger than either the river or the swimmer's velocity, right? And that's of course because the river and the swimmer's velocity make up the legs of that right triangle, and the hypotenuse is always larger than either of its legs. So that makes sense. Now the next part of the question says, how far downstream do they end up when they reach the opposite side if the river is 10 meters wide? So our strategy here is we find the time that it would take them to swim across the river if the river were completely still. If it weren't a river, if it were a pond, for example, we see how long it would take them to traverse that river. That's the y motion. And then we're going to use that time that we find to find out how far the river carries them downstream. So we treat x and y motion independently here, okay? There's certain assumptions that you have to do to make that, but that's what we've been doing all along. So we're going to continue with those assumptions. So let's first use y to find the time. This is a situation where the acceleration is 0. So we can just use the definition of the average velocity. The definition of the average velocity says that it's equal to the displacement divided by the time. Since we're only considering y motion, that displacement is the change in y that it makes divided by the change in time. Now the change in y that it makes is 10 meters because that's the width of the river. And so here we have 1.7 meters per second is equal to 10 meters divided by delta t, where delta t is that change in time. If you solve by cross multiplying, you end up with a delta t of 5.9 seconds. So that's how long it takes that person to swim across the river. Now we use the x motion equations to find the distance that the person is swept downstream while they're swimming. Yet again, since there's no acceleration, we can just use the definition of the average velocity to do this. Here we have v average in the x direction is equal to the change in x divided by the change in time. The change in x is what we're trying to solve for. That's how far they get swept down the river. And the change in time is what we found previously, which is 5.9 seconds. The velocity of the river, remember, is 2 meters per second. So by cross multiplying, you can solve for delta x, and delta x gives you 11.8 meters. So that's how far the person is swept downstream while they're swimming. So when they finish, they end up across the river, sure, but about 11.8 meters downstream from where they started according to the origin. I hope that's clear. If you have any questions, don't hesitate to ask me in class, and I'll see you then.